If we look at question 1, we've got a scientist investigating the radiation emitted by different radioactive isotopes. We're starting off with polonium-210, and it's saying the radiation emitted by it can be represented by the symbol He with the 4 and the 2. What type of radiation can be represented by that? Now, there is only one option, and that of course is alpha. That's our alpha particle. Sometimes it's given the sign alpha and a 4-2, but of late the exam board seems to be liking using the helium symbol. Things to note from that is this is not an atom of helium, it's a helium nucleus. 1.2. How many protons are there in a particle of radiation represented by 4 and 2? Now, remember, the 4 is the atomic mass. In a way, the 2 is the atomic number. The atomic number is also the proton number. So again, only one possible answer, and that would be 2. Question 1.3. We've got a polonium-210 nucleus, breaks down into a lead nucleus by emitting the alpha particle, and it's shown by the nuclear equation. What is the value of X? Now, you've got to remember that this is being emitted from the nucleus, so we're losing a mass of 4, so we can see that it goes from 210 down to 206, which means that we've got to take 2 off the bottom number, so we're losing 2 protons, which means that we're going from 84 down to 82. So again, there's only one possible answer there. And then 1.4, the sample of polonium-210 had an activity of 100 becquerels. Complete the sentence, and we've got some options from the box. After 1 half-life, the activity of polonium-210 in the sample was what? Now, you've got to remember that half-life is the time it takes for half the radioactive nuclei to break down. So if our sample has gone through 1 half-life, it means that we have to half 100 becquerels. We have only got one possible answer there, and it's got to be 50. So there's our 50, and there's another nice mark to get. Now, the scientist investigated another radioactive isotope that was a source of gamma radiation, and we've got a diagram of the equipment used. Now, the count rate is a number of counts detected each second. In 30 seconds, the number of counts detected was 1,500. We need to calculate the count rate. Now, you've got 1,500 counts in 30 seconds. We need to work out how many in 1 second. That means we need to divide 1,500 by 30. You would put those numbers into your calculator, and that would give you an answer of 50 counts. And again, that's 2 marks, which is more of a maths question than anything else. Now, the scientists placed a thick sheet of lead between the source of gamma radiation and the detector. Now, what was the effect of the sheet of lead on the count rate, and give a reason for your answer. Now, the effect would be that the count rate would decrease. Now, they would accept that the count rate would drop to almost 0, but it would definitely be decreased because our lead will absorb the gamma radiation. Now, the best answer is to say that gamma is absorbed by lead, which has the symbol PB. Now, you can also talk about the fact that gamma is blocked by lead. That would also be a completely acceptable answer. You could also talk about the fact that gamma cannot penetrate through thick lead, and so on. So make sure you're quite clear on that one. So count rate doesn't necessarily go down to completely 0, but it is very much reduced. 1.7. The lead was irradiated by the gamma radiation. So what happened to the lead when it was irradiated by the gamma radiation? Now, certainly when this was used in the exam, a lot of people got this question incorrect. Now, if you are irradiated, it just means that you are being exposed to that radiation. So lead doesn't become radioactive as a result of it. The lead certainly doesn't gain anything from gamma. Remember, gamma is just an electromagnetic wave. So it means that our only option there is that the lead was exposed to the gamma radiation. 1.8. Gamma radiation is emitted from the nucleus of an atom. We've got to complete the sentence now. I've already answered this question from earlier. Gamma radiation consists of, again, there's only one possible answer. It's our electromagnetic wave. Remember, gamma is different from alpha and beta because it's a wave. Alpha and beta are actual particles. Now, 1.9. The scientists suggest one reason why using long tongues rather than short tongues was safe for the scientist. Really need to be just saying that the longer tongues keep the radioactive source further away from the scientist, so it reduces the risk of any cancers, any mutations from the radioactivity. So you need to be making the point that you are reducing the amount of radiation that the scientist is exposed to. You can't say that it stops the scientist being irradiated. That's just not true. It just keeps the radioactivity further away from the person. Okay, and that's your first question done. It's out of 11. Hopefully you've got 11 out of 11 on that one. Right, on question 2. Now, here we've got a person using a zip wire going from the tree to the ground. Now, as a person moves down the zip wire, the block moves downwards. What happens to the gravitational potential and energy of the person as a person accelerates down the zip wire? Now, in this case, the person is going down, so their store of gravitational potential energy can only be decreasing. So make sure you got that clear in your head. So as the person moves closer to the ground, their gravitational store reduces. And then 2.2, what happens to the kinetic energy of the person as they accelerate down the zip wire? Now, of course, hopefully you've realised that that gravitational store of energy that's decreasing is being transferred into the kinetic store. So it means that as the person moves further down the zip wire, more and more energy, store of energy is transferred, therefore the kinetic store is increasing. The person is going faster and faster. And then question 2.3, bit of a maths question, but this one's nice to you because they actually give you the formula. So here we're just going to substitute the numbers that we've got. So we've got a starting height of 3.4 meters above the ground. You're given the mass of the block, and in all these questions they always give you the gravitational field strength of 9.8 newtons per kilogram. We've got to calculate the gravitational potential energy of the block, and we need to use the equation. So in this case, we need to work out EP, and then just substitute the numbers in that we've got. We've got a mass of 2.5 multiplied by 9.8, and then that's multiplied by the height, which is 3.4 meters. You got your first mark just by doing that. Then put those numbers into your calculator, and that will give you an answer of 83.3 joules. Now, if you rounded that to a whole number, and you got 83, that would also give you the second mark. So I would suggest that you always show your working out, just in case you make a mistake with your calculator, you'll get your working out marks. 2 nice marks to pick up. And then question 2.4. So now we're going to try and calculate the kinetic store of energy. Calculate the maximum kinetic energy of the block. Now, again, we've been given the equation. We just need to make sure that we're highlighting the numbers we need. So we've got a maximum speed. We've got the mass of the block. And then from there, we just need to substitute those numbers in. So the kinetic energy is what we're trying to find out. So that's EK. And that is a half times the mass, which is 2.5, multiplied by the speed squared. Now, if you're going to go wrong anywhere, it's normally because people forget to square the speed. So again, put these numbers into your calculator carefully, and if you do that, you should end up with the answer of 28.8 joules. Now it is acceptable if you rounded up your answer to 29 joules, you would still get the credit for it. And then on question 2.5, as the trolley moves, work is done against friction. What is the effect of this? Now, obviously that first answer is ridiculous. Conservation of energy can't be created or destroyed, so we know straight away that answer is absolute rubbish. Some energy is transferred to the surroundings. Okay, that's definitely possible, and the total energy of the block and the trolley increases. Well, again, that's linked to the first one. Energy can't be created, sorry, it can't be destroyed, but it can't be created either. That's suggesting we're creating energy, so it means that the middle answer has to be the correct one. So some energy is transferred to the surroundings. So you think about it, that friction is, I suppose, an unwanted energy transfer, and it will warm up the surface that the trolley is moving along. And then on 2.6, the person oils the wheels on the trolley. Explain how this will affect the speed of the person down the zip wire. Now on this one, make sure you get the first obvious mark. How will this affect the speed? So the first thing to say is the speed will increase. The second mark is to do with explaining why the person goes faster. Well, it's because the friction is reduced due to the oiling of the wheels. So you could talk about, because work is done, the work done against friction is reduced. That could be a way to put it. If you just say that there's less friction, you'll get the second mark on that one. That is worth maximum of 9 marks. So if you got 9 out of 9 on that particular question. Okay, question 3. We've got a piece of steel is heated until it has all melted. So this time we've got to calculate the change in thermal energy when the temperature of the piece of steel is increased by 50 degrees centigrade. So that's an important bit of data. We've got the mass of steel, 4 kilograms, and we've got the specific heat capacity of steel, which is 420 joules per kilogram per degree centigrade. We don't even have to look for the equation, it's given to us. So here it's a 2 marker, so it just means that we're just going to multiply through. So our change in thermal energy, so change in energy equals, well, we've got a mass of 4, multiplied by the specific heat capacity, 420, multiplied by the change in temperature. The temperature is increased by 50 degrees. And it's just a case of put those numbers into your calculator, and then you get the answer of 84,000 joules. Make sure you get the right number of zeros on the end there. 3.2. The internal energy of the steel increases as the steel is heated. What is meant by the internal energy of steel? Now, the change in energy of the steel particles as the steel melts, that's definitely not the case. The energy added to the steel particles as they are heated, that's not correct either. So the total kinetic energy and the potential energy of the steel particles, that is basically the internal energy. So it's a combination of pretty much the movement of those particles and the position they are on that material. So the last option is the only correct option on that. Question 3.3. Now, solid steel cannot be poured. Which statement about the particles in a solid gives the reason why? The number of particles always stays the same. Well, that is correct, but it's got nothing to do with why steel is a solid. The particles are close together. That's true, but they're also close together in a liquid, so that's not necessarily the best answer. The particles have a fixed size. Well, generally that's true. Our molecules are generally the same size no matter what state they're in, So it means that our particles are in fixed positions. That's why solids keep their shape. And now on 3.4, choose the answer. We've got to choose the answer from the box. As a piece of solid steel melts, the mass of the steel. Well, just because we're changing the state, the number of particles isn't changing. So the only answer we can go for here is stays the same. Question 3.5. Which diagram shows the arrangement of particles and how to change when a solid melts and becomes a liquid? That one, we should know that in our solid state we've got those nice neat rows and we're just becoming slightly more random arrangements, so it has to be that top box. So again, nice easy mark to get. 3.6. The density of steel decreases as it melts. That's because we are getting our particles spreading out more. So how does the spacing of the particles change as the steel melts? In this case, and it's important that you're actually answering the question, a lot of people in the 2023 exam, although implied they knew what they were talking about, didn't get the mark because they need to be talking about the spacing. So how do the spacing of the particles change? Well, the spacing increases. And that's what you need to be talking. Or talk about how the particles move further apart. They were the only acceptable answers to get the mark, and you'd be amazed at the number of people who didn't get the mark in that particular question. And now on 3.7, choose the answer from the box again. So we've got one of three possible choices. Melting is an example of what type of change? Well, melting is definitely not a chemical reaction, so we can get rid of that answer. Melting is an example of a permanent change. Well, that's a load of rubbish as well, because we could just kind of start cooling the temperature and we go back into a solid. So again, the only correct answer is a physical change. And there's another mark. Right, now here we've got a question about steel. It's a mixture of iron and a small amount of carbon. We've got a table showing the mass of carbon in 1 kilogram of different types of steel. Now we're being told a 4 kilogram piece of steel contains 18 grams of carbon. Determine which type of steel the 4 kilogram piece is made from. You should include a calculation in your answer. Now, in this one, if you didn't include a calculation in your answer, you would score no marks, even if you just happen to guess the correct type of carbon. Now, there's two ways you can go about answering this question. You could have a look at the mass of carbon per kilogram of steel. Now, we've got a 4 kilogram piece of steel containing 18 grams of carbon. Well, how much carbon do we have in 1 kilogram? To do that, the calculation we do is 18 divided by 4. That would give you 4.5 grams per kilogram. If you look at the table, you've got 4.5 grams of steel in our medium carbon, and we need to write that in as our answer. So medium carbon, that has got us 3 marks, as simple as that. Now the other approach to take could be is determine which type of steel. So we've got a 4 kilogram block. Well, if you had low carbon, you've got 2 grams per kilogram, multiply that by 4. That gives you 8 grams. Multiply 4.5 by the 4 kilograms, that gives us 18 grams. And then the last one, multiply that by 4, gives us 28 grams. Well, we're being told we've got 18 grams of carbon in that steel. So again, you can use that way of checking your answer. Either calculation that you use, as long as you've got the medium carbon, you've got your 3 marks really. That particular question, the way it was set up, you pretty much either got 0 marks or 3 marks on it. So when it said things like you should include a calculation in your answer, that's a big hint. It's the only way to get all the marks possible. Right, now we're up to a 3-mark question now, which is very generous for this particular calculation. So we've got the same 4 kilogram piece of solid steel was heated until it reached its melting point. The additional energy required to melt the piece of steel was 280,000 joules. Calculate the specific latent heat of fusion of the steel. Use the physics equation sheet. Now the good thing with this one is that whether they give you the full equation sheet or not, this equation will always be there. The equation which you need to find is energy equals mass times the latent heat of fusion. So it's quite a simple formula. Now this question is worth 3 marks because this time we're not just substituting numbers in and just multiplying through. We have to do some kind of rearrangement. So the energy we use was 280,000. We've got a mass of 4 kilograms. Substitute your numbers in. You've got 280,000 equals the mass of 4 multiplied by L. We need to get L by itself, so we divide both sides by 4. That means that our L equals 280,000 divided by 4. Put those numbers into your calculator and you should get the answer of 70,000 joules per kilogram. Again, be careful making sure that you're copying down the correct number of zeros off your calculator. Don't lose marks after doing all that hard work. But essentially with this question, you don't get a mark for getting the formula, but you do get the first mark for substituting numbers in correctly. The second mark for the rearrangement, getting L by itself, the latent heat of fusion, and then of course the third mark is getting the answer correct. And that's the end of that particular question. Now question 4, we're into our circuit. So a gardener wanted to build an electrical circuit to monitor the temperature in a greenhouse. Which symbol represents an electrical component with a resistance that decreases as the temperature increases? This is our thermistor, which is that symbol. This is just a case of making sure you know your circuit symbols. Now when the resistance of an electrical circuit decreases, the current in the circuit increases. Complete the sentence. And this is to do with what is an electric current. It's a flow of what? Well, the only answer we've got here is it is a flow of charge. That's it, that's our definition. Again, it's a definition you need to know. Now, this question is 4-marker, and there's certain things you have to include in your answer to make sure you're getting all the answers. Now, again, it's one of those questions where they're giving you the pictures of the equipment, and really you need to be saying what you do with each bit of equipment alongside your method. Now, the resistant meter displays the resistance of the component. That's an important bit because the gardener is investigating how the resistance of the component varies with temperature. There's a bit of a clue there, that's why you've got your thermometer. Now, the first thing to do would be to place the component or the thermistor in the water, well, the beaker really. So we're starting off with the iced water. So of course we need to measure that. Now we also need to record the temperature using the thermometer of the temperature of that water in the beaker. So remember, be specific. You might think it's really obvious you measure temperature with a thermometer, but you need to specify it. So remember, it's asking how to use the equipment. So once we've got the temperature, we then need to look at the resistance meter and record the resistance. So we've measured the temperature with the thermometer, we've measured the resistance using the resistance meter of our beaker of iced water. We've now got 3 marks from that. And then the final bit is why we've got the kettle. Well, we're going to use some hot water to change the temperature, and then The fourth mark comes from saying that you need to repeat the investigation, but this time use hot water from the kettle, but measure your resistance and your temperature at the same time. That's where your 4 marks comes from. Make it easy for yourself, make it easy for the person marking this. Bullet point your answer. Makes life a lot easier. Right, and then we've got a graph showing how the resistance of the component varies with temperature. We've got to choose again an answer from the box about the relationship between the temperature and the resistance of the components. Now, linear is talking about things which go in lines, straight lines. Well, it's clearly not a straight line, so that is incorrect. If you look at directly proportional, again, that is all to do with having a straight line that starts from the origin. Well, this is the complete opposite, so that is incorrect. Non-linear, non-straight line, that is our only answer possible. And there's a nice straightforward, easy mark, I'm hoping. Okay, question 4.5. Now the temperature in the greenhouse changed from 10 degrees to 30 degrees centigrade. We've got to determine the change in resistance of the component between these temperatures. There's a big hint. Use figure 5, which I've got the graph at the bottom of the page, kind of repeated just to make it a bit easier for you. Now, what you need to know is how much did the resistance change by? Well, we need to know what the resistance was at 10 degrees and what the resistance was at 30 degrees. And this is where we need to use our graph. So you need to get your ruler and draw a line up from 10 degrees till it hits the curve, and then draw across. So at 10 degrees our resistance was 200 ohms. Now at 30 degrees, if we draw our line up to the line, and this is where you just need to read off the scale carefully. Remember, each of the little squares here is worth 10 ohms. So by my reckoning, that goes to 80. We need to look at the change in resistance. Well, the change is going from 200 down to 80, so the difference is 120 ohms. So take the 80 from the 200, there's our change in resistance. 2 marks. 1 mark really for getting the data accurately off the graph, 2nd mark for actually getting the correct answer on that one. Now the gardener builds a circuit that switches a heater on when the greenhouse gets too cold. Now it's asking us to use a physics equations sheet to answer the next 2 questions. Now that's likely to change for next year because you'll be expected to know these formulas, learn these formulas as things stand at the minute. Now this one, you just have to remember that power equals potential difference times current. You can write this as symbols, you can write it as full words, it's up to you. Personally, I just reckon that it's much easier to remember the symbols. It's less to have to remember. Now, we need to use that formula on this next part of the question. Obviously, if you don't know the formula, you aren't going to do particularly well in the next question because you'll not be able to calculate it. Now, this is worth 3 marks, and we'll go through the reasons why. We're given the power, we're given the potential difference, we've got to work out the current. So at this point we need to substitute our numbers in to P equals VI. We've got power of 2,900 equals a potential difference of 230, and I, the current, is what we're trying to work out. We've got our first mark for just substituting our numbers incorrectly. We now need to get I by itself, so we need to divide both sides by 230. That means current is 2,900 divided by 230. Now, if you put those numbers into your calculator, you get an answer which, if you round it to 1 decimal place, gives you 12.6 amperes. Now, if you rounded that to 13 amperes, you would still get the mark. But, with this, make sure you're confident being able to manipulate the equation once you've substituted your numbers in. Don't lose marks on making silly mistakes on that one. That whole question is out of 13. Hopefully you got 13 out of 13. Now question 5, this is where we're looking at wind power and solar panel. They're both renewable energy resources used to generate electricity for the national grid. We've got a list which of the following is also a renewable energy resource. Now, if you remember, natural gas is a fossil fuel. We're running out of our fossil fuels, so clearly non-renewable. You've got your 3 fossil fuels: coal, oil and gas. Coal, oil and gas, I should say. And the 4th non-renewable energy source is nuclear fuel. So that one's going to be wrong as well. So geothermal, using the heat from the rocks underground, that is very much renewable. This one, question 5.2, is just knowing your prefixes. Giga, which of the following is the same as 36 gigajoules? Now, if you've got kilojoules, that's 10 to the 3, so that one's going to be incorrect. Mega is a million, so that's 10 to the 6 is incorrect. Giga is the next scale up, so it is 36 times 10 to the 9. That's quite a lot of energy. Now this question, there is lots you can write about in this question, and there's 2 parts to it. So if you want to get full marks on this, you do really need to be talking about both graphs. Now, where a lot of people restricted themselves to a maximum of 2 marks in 2023 was all they did was just describe the actual graphs, describing the graphs well, and that is limiting you to 2 marks. There was no idea of comparing the energy generated from kind of wind and solar, which is quite restrictive. If you start doing a bit of a comparison, you're getting into your level 2 answer for 3 to 4 marks. But if you want to get your kind of hard, your level 3 answer, 5 and 6 marks, you have to be trying to explain why these trends are there in the graphs. So if we take figure 6 to begin with, now this is looking at the energy, the power generated, comparing solar power with wind power from 2014 to 2019. Now you can see quite clearly, and I would include numbers in your answer, that your wind power back in 2014 starts off at 3,000 megawatts here, and we get a gradual increase, or the trend is upwards until 2019, where that goes up to 7,200 megawatts. There's a little bit of a dip in 2016. If we're talking about wind power, 2016 may not have been as windy a year as certainly the year before it. Certainly 2017 was a windier year. Now, why did we get an increase from 2014 to 2019? Well, it's probably not because the country is necessarily getting windier, although you could talk about climate change, more extreme weathers. That would actually give you some credit. However, the more sensible answer is we have built more wind turbines. If we've built more wind turbines, we're going to produce more power from them. Now, if we're going to talk about the trend with solar power, that starts off quite low. If I remember rightly, it's about 400 megawatts in 2014, and that has a very gradual increase until 2019, and we get to 1,400 megawatts. But that is an upward trend. Now, again, it's unlikely that the UK has necessarily got sunnier in those times. We just have more solar panels. So that explains why we have that increase. Now, obviously, we need to be comparing this, and if you make the point that we are always generating more energy from wind power year by year than we do by solar power, again, that's a comparison. There's a clear difference. So again, include that in your answer, particularly if you're looking for your higher marks. Now, Don't forget to talk about figure 7 as well. Now this is looking at the trends of generating power from wind and solar over the year. So again, you can describe the trends, the fact that wind power starts off high in January, gradually dips down to a low in July, and then increases again through up to kind of November, where it's at its peak. At the same time, solar power starts low in January, gradually builds up through April and May, and it's at the peak during June and July, and then after that drops down again and is at quite a low point in December. Now that's just describing the graph. You can talk about the fact that wind power is generally always producing more power, apart from in that month of July, where there's actually more energy generated by solar power than the wind. So talk about those trends. Now the explanation why. Now it isn't just a case of the weather isn't very good. You need to be talking about the fact that generally in the winter the weather is windier. More wind means more energy or power is being generated. So if you think about it, the winter and autumn months, lots of winds, lots of energy generated. Generally in the summer months, June and July, you don't get as much wind. On the flip side, why does solar power increase, or the power generated from solar power increase in the summer months? Well, theoretically they should be the sunnier months, so we have longer hours of daylight. Theoretically we should have more sunshine in those months. January and, well, if you look at the extremes, January and December, that's generally the months where we have a lot less sunshine, a lot less hours of sunshine. Also the light intensity is a lot less, so we generate less power. So if you're after those kind of 6 marks, you need to be not just describing the 2 graphs, that's your level 1. The comparison between the solar and wind would get you into the level 2, but you need to be explaining why the differences. So in figure 6 we need to be talking about the fact that the trends are upwards because we're building more wind turbines, we're building more solar panels. In figure 7 we generate more more solar power in the summer when the sun is out more intense of a sun, and don't forget about the windier months through the autumn in the winter. That's where you get the 6 marks from. Right, and then question 6, final question. Now this question comes up frequently about placing a voltmeter in the correct place. Now before we get to that, this question is all about using it's our body analysis scales. So by using the electrical resistance of a person's legs, you can estimate the percentage of water in the person's body. Obviously your legs contain both solid tissue and water, and the student used resistors to model the solid tissue and water. The student connected a 20 ohm resistor in parallel with resistor R. So we've got the circuit diagram. We'll come back to that shortly, but first of all, to determine the total resistance of both the resistors, a voltmeter must be connected into the circuit. Complete figure 9 to show where the voltmeter should be connected. Now we need the potential difference across the resistors, so the best place to put your voltmeter would be completely around both resistors. Now the other place which the mark scheme allows would be to connect the voltmeter across your kind of power pack, because that will still give you the same reading in this particular case. I would say this is your best answer, but you'd also get marks for the other answer as well. Now in question 6.2, the student calculated the total resistance of the 2 resistors. The student's answer was 26 ohms. Explain why the student's answer cannot be correct. Now just to remind you, on this particular part of the circuit, the resistors are in parallel. And that's the important point to remember. So we've got a 20 ohm resistor, and we've got resistor R that we don't know about. Now the thing we've got to remember is that in a parallel circuit, particularly when we've got resistors in parallel, that the total resistance is less than the value of the lowest resistor. Now, taking that into account, the only number we've got here is that 20 ohms. So the only thing we know for sure is that the total resistance has to be less than 20 ohms in this circuit. And the reason being, as I've just said, is that the total resistance of the resistors in parallel is always less than the resistance of the smallest resistor. Therefore, it has to be less than 20 ohms. Then, question 6.3. This equation comes up all the time, and going forward, you're going to have to learn these formulae. So, bearing in mind in 2023, pupils did actually have that formula sheet. So we can get rid, so ignore that bit, you just need to know these formulas. And this formula in particular comes up all the time. V equals IR. Potential difference equals current times resistance. You just need to know that formula. Now, obviously, look at 6.4. You cannot get the 3 marks if you don't know that formula in 6.3. So we've got V equals IR again. We've got to calculate the potential difference across the 2 resistors. Now we're being told that we've got 7.5 ohms of resistance. We've got a current of 420 milliamperes. This is a catch, and a lot of people miss this. 480 milliamperes. Milli means that you've got 1000 milliamperes make up 1 ampere. When we're doing these calculations, our current needs to be in amperes, not milliamperes. So to go from milliamperes back to our amperes, we divide by 1000. That means that in this case, our current, 480 milliamperes, equals 0.480 amperes. Once we've got that bit done, the rest of it should be plain sailing, and we just put our numbers into the formula. And from there you got V equals IR, so it means that V equals I, which is now 0.480, multiplied by our resistance of 7.5. Put those numbers in your calculator, and you get a potential difference of 3.6 volts. Now, you need to get kind of a bit savvy about this. This is worth 3 marks. Bearing in mind, we're just calculating kind of V, so it's just V equals I multiplied by R. The fact that they're giving you 3 marks means there's got to be a catch somewhere, and in this case, it's that conversion. So, be suspicious if they're being very generous with the marks. Now, obviously, if you don't convert your answer and you used 480 in this particular calculation, you would end up with an answer out by a factor of 1000. So if you got 3600 volts, which is where you haven't converted the current, you would still pick up 2 marks. But we want to make sure we're picking up all the marks. So be suspicious and convert the numbers when you need to. So now we've got the student investigated how the resistance of R affected the total resistance of the circuit, and then we've got some results. Some of the results are plotted on the graph. Now this graph question, you should be looking at 4 easy marks. Now on 6.5, we've got to finish off figure 10. Label both axes. Now if you look at the x-axis, this is going up in nice regular 5s. Well, that's our x-axis. Now whatever is written as a label in the table, that is the label you should put on your axis. So this one is resistance of R in ohms. And likewise for the y-axis, just copy down exactly the label there. So you've got total resistance of the circuit in ohms. So just copy it down, don't change it, don't start abbreviating it, and make sure you include the units. That's 1 mark done. So tick that bit as a bit of a checklist that you've done it. Plot the 2 remaining values from table 2. So we need to plot the value for 15 now. If you're going to lose a mark, this is where people lost the mark. At 15, right, we'll go up to 8. Well, we've got to go up to 8.6. Now, each of the small squares is worth 0.2 of an ohm. So we need to go 3 of the small squares up. So we have a nice little cross there. Remember, you need to be accurate with it. If you're more than half a square out, unfortunately, you lose a mark. The second point is right on 10. So this one is a little bit easier to plot. Now, here we've got this nice curve. So what we need to do is we need to, in fact, let's just tick off, we've plotted our graph. Now we need to draw the line of best fit. Now, a lot of people lost a mark by drawing this as a straight line. In this case, there's a clear curve to it. So what you need to do, just get your pencil and you need to make sure you're going through all the points. There is our 3rd mark. Now, again, another good way to lose a mark is if you do a dot to dot with a ruler. So if you did each bit as a straight line, you didn't get the mark on this one. So again, don't lose out on a relatively simple mark. Now, 6.6, what resistance of R would give a total resistance of 4.4 ohms? So we're looking for the total resistance, and again, you need to be able to use a scale. So this is 2 squares up from 4. Draw that line across to the graph, and then, of course, draw it down where it hits. Now, if you've got this drawn correctly, this should be 1 small square to the right of 5. That means your answer is 5.5 ohms. They gave a tolerance of half a small square on this, and if you did plot the graph incorrectly and get your line of best fit incorrect, the examiners actually looked at your line, and if you show you're working out, as we've done kind of here, and you then read off the answer correctly off this scale, you could still get the mark, even though your answer might not technically be correct. They didn't penalise you more than once for drawing the graph badly. You should be looking at your graph questions as being guaranteed easy marks every time. Alright, so now we are almost there. The body analysis scales initially show a reading of 0 kilograms. When the student steps onto the scales, the reading is 64.8 kilograms. The student steps off the scales and then immediately steps back on. The scales now show a reading of 64.1 kilograms. So we need to complete the sentence. Now, the difference between the 2 values given by the scales is what type of error. In this case, it's not a 0 error because the scales went back to 0. It is just a random error, one of those things. That was the only acceptable answer there. Now, final question. This not many people got all 3 marks on this one. Now, the total resistance of the student's legs is 600 kilo ohms. Now, the healthy body percentage is between 45% and 65%. The different measurements of the mass of the student mean that the student could be in either category A or category B. You need to evaluate if the student has a healthy body water percentage. Now, the first thing you needed to do to get the first mark was, well, in fact, you need to use the graph, which is why it's repeated down here at the bottom. So if you draw up a line from 600 kilo ohms. Now, if you draw it all the way up to the top, we're only really interested in the data for A and B. Now, if you draw the line across for person A, now it's much easier with a ruler. Now, person A, and by that calculation, has the body fat percentage, sorry, a water percentage of 61%. Now, person B, again, if you look at the graph and draw the line across, and it's much easier when you've got a ruler, person B has a water percentage of 68%. Now, obviously it's saying here that the healthy body water percentage has to be between 45% and 65%. Now, to pick up the third mark, you have to make points that if the student was in category A, they fall within the healthy limit of body water percentage. However, if they fall into category B, they're slightly above the healthy water percentage, therefore would be classed as unhealthy. And that's where the third mark came from. So, like I said, the first 2 marks, calculate the water percentage for A, 1 mark. Second mark, work it out for B, and then make the points that whichever category, it could be healthy, it could be unhealthy, depending on whether the person is actually in category A or B. That question was worth 15 marks, and that brings us to the end of this particular exam paper. Hopefully you got 70 out of 70. If you did, well done.